Polynomial functions. So polynomial functions, you got a little vocabulary sheet of all the different things of polynomial functions. We're going to use a lot of those things today. Not quite all of them, but a lot of those things we'll talk about today. A polynomial function. An example of a polynomial function would be something like f of x is equal to 3x cubed minus 5x squared plus 7x minus 10, something like that. That's an example of a polynomial function. Notice how that it is written in descending order. From highest power of x down. That's how we always write them. That's the way we want them written. So when you're writing your polynomials, you want them in descending order. And the key things there with that is making sure it's in order so that your leading coefficient is in front of the degree term. So those are things that are right there on the top two boxes of your vocabulary sheet there. I'm referencing that thing because I put so much work into that. So leading coefficient for this particular polynomial would be 3. The degree would also be 3, but it's from the exponent on the variable, okay, is where that degree is coming from. You probably remember a lot of this from Algebra 2. Now, your textbook, when it talks about the standard form, and I mention this so that you don't get confused when you look at it, or if there's a question about it. The standard form is written like this, and it's a lot of notation. It's using subscripts and superscripts or exponents. And then it puts an ellipses in the middle there. The 3 dots, that's an ellipses. It looks intimidating like this. All you need to know is that the A's are the coefficients. So this is x to the nth power. That's the nth degree polynomial. That's the highest power of x. Then it's the next highest power of x as you subtract 1. Look at our example. X cubed, the 3 is the n. N minus 1 was 2. N minus 2 was 1. N minus 3. It's a fancy way of writing, hey, put it in descending order. That's all that it says. Okay. That's more of a college level notation style thing. So you're in a college textbook. So when they throw that stuff at you, you got to learn to kind of read it and know what it is. So just think about it. Hey, x is my variable. So anything with an exponent, that's just an exponent on x. And they're just going down. So it starts at n and goes down 1 every time. So they're just saying put it in descending order. You got numbers in the front. The A's are just numbers. The coefficients for those terms. That's all that says. Okay. So you've seen standard form. Just know it means put it in descending order, like we already knew how to do. Okay. Nothing new under the sun, as they say. So there are some rules to being classified as a polynomial. Okay. There's not many rules. There's only 3. The first one being that you have integer exponents. That means no fractions on the exponents or radicals. If you remember from Algebra 2, fraction exponents and radicals are the same thing. So I'm going to be a little bit redundant there. No fraction exponents, no radicals in a polynomial. Okay, polynomial has integer exponents only. Okay, and kind of I almost want to put it in the same rule, But integer exponents, that just says, okay, no fractions, no radicals. But then it has positive exponents only. So really, it's whole number exponents is really what that tells us. That your textbook, the author separates those two things into two rules. I think you could set it into one rule and say it's whole number exponents. The third rule, the last one, is division by an expression with a variable is not allowed. So to be a polynomial, you can't have a variable in the denominator. That would be something like x squared minus 5 divided by x cubed plus 2. That is not a polynomial function. It may be a function, but it's not a polynomial function. That right there is a violation of Rule 3. You cannot have x's in the denominator. You can have fraction coefficients. You can't have fraction exponents. You can have fractions in the problem, but they cannot have x's in the denominator. Maybe that's what you need to write, maybe instead of that big long word there. No variables in the denominator of a fraction. That's probably the easier way to remember that. No x's in the denominator. We will do, in chapter 5, we will do polynomial, rational polynomial functions where they actually do allow the x's in the denominator, but that's a rational function, not a polynomial function. So rational functions, you'll get a new vocabulary list for that. You did not do those in Algebra 2. So that's going to be a new thing. So that's one of the very few things that was not in Algebra 2 that is in college algebra. Okay. Now, we talked about earlier the degree and the leading coefficient. So let's write those things down there. Degree, that's your highest power of x. Or highest power of your variable, whatever the variable is. The leading coefficient. Number in front of the highest power of x. Read a little bit more on your vocabulary list there. Degree, the highest power of the variable in the polynomial. It indicates your end behavior. We'll talk about that later. Leading coefficient is the coefficient to the term with the highest degree. It influences the graph's orientation, which is also end behavior. So when we talk about end behavior, those two things are going to be the most important parts. Okay, so and you may remember that from Algebra 2. When we get to it, you'll probably will remember it. Okay, so those two pieces are very important when it comes to how the graph looks. They have the highest power, so they influence the graph more than anything else. Just like in society, people with power influence things more than anybody else does, right? People with power. Here, Mr. Killingsworth tends to influence things the most. He has the most power around here, in our building anyway. So he influences the teachers influence the kids influence each other, and it's all a big circle. All right, so let's talk about transformations. So polynomial transformations. Example A, describe transformations on f of x is equal to x to the fourth power. So the parent graph is x to the fourth power. So we did transformations on all different kinds of functions back in chapter 3. So here we're doing it to polynomial functions. The parent graph is x to the fourth. If I look at the graph of the parent graph here, x raised to the fourth, it looks a lot like a parabola. It's just a little flatter on the bottom. It's not completely flat. It's just wider at the bottom. A parabola is a little bit more pointy there, still round but pointed, kind of more of a shovel type shape there from the x to the fourth graph. That's what the parent graph looks like. Here's the equation. 1/2 x minus 1 to the fourth plus 3. When we talked about transformations back in chapter 3, we talked about the fact that the rules are the same no matter what kind of function you're dealing with. So these transformations are going to be the same as they were in chapter 3 when we were dealing with square root functions, we were dealing with absolute value functions, we were dealing with quadratics. All the transformations are the same rules. So what transformations have happened to the parent graph here based on this equation? All right, so they have the minus 1 is right 1. The plus 3 is going to be up 3. A vertical compression by a factor of 1/2. So y'all remember those rules from there. We're still using the same rules. Nothing's changed. So this is easy stuff because we've done it, 2 chapters in a row. This makes 3. We did those different transformations. Really easy stuff. Same rules. Describe the transformations on the parent graph of x to the fourth for -2, x plus 5 to the fourth power minus 8. What transformations occurred there? Okay, so the minus sign out in the front is a reflection over the x-axis. Okay, that's good. What else? Yeah, that 2 is a vertical stretch because it's a multiplier on the outside that's bigger than 1. Yeah, the plus 5 on the inside, that's a left 5. And then down 8. So the minus 8 is down 8. Realize I could change the parent function to an x cubed, x to the 5th power, x to the 18th power. It doesn't matter what the parent function is. The transformation rules are the same. Find that transformations page is the same rules. Okay, no, the parent function just is the only thing that's changing. And in Algebra 2, we tended to focus more on x to the 3rd powers things as our polynomials. In college algebra, we'll get a little bit bigger. We'll get x to the 4th, x to the 5th kind of stuff in there. Still doing some cubics, but x to the 3rd and x to the 4th, x to the 5th. Don't generally get much bigger than that because it gets super long if you do. It's not any harder, it's just longer out of that. So, but transformation rules don't change. No matter what the parent function is, the rules are the same. So just know those rules and you got it made there. So that's easy enough. Moving on. So zeros of a polynomial. What's another word for zeros? Remember from maybe quadratics. Huh? What intercepts? X-intercepts. What's another word for that? There's a couple more that we may have used in the past. Roots. Solutions. All of those words mean the same thing. Okay, so Khan Academy tends to use different words than our textbook uses, but anywhere you go, if you say zeros, you could also say x-intercepts if it's a real number, You could say roots, whether it's real or complex. You could say solutions, whether it's real or complex. Okay, so x-intercepts implies it's a real number. It doesn't have the I in it. Remember the complex numbers with the I's? You don't have that if it's an x-intercept. But if it's a zero, a root, or a solution, you could have the I in there. Okay, so but they all mean the same things. So those are all words synonymous with the zeros of a polynomial. Relate to the factors and intercepts when the function equals 0. Okay. So we're going to be doing some factoring in this. We'll start out with some that are already factored for us, and go from there. So let's find the zeros of a polynomial or of the polynomial. Example C. Here's our polynomial. F of x is equal to 5x squared, parentheses, x plus 2, parentheses, 2x minus 1 to the fourth. So that's our polynomial. We want to find the zeros of that. So to find the zeros of any equation ever, you set the whole equation equal to 0. So when you're reading the problem out of the book, I would probably just start my first step setting it equal to 0 like that. Okay. And in Algebra 1 and Algebra 2, we learned a thing called the zero product property, which said if you multiplied more than one thing together and it equaled 0, then at least one of those things was 0. If they all have variables in them, then you've got to set them all equal to 0 to find out what x values would give you 0 out of that. Because if this first term, 5x squared, was 0, then everything 0 times everything else is still 0. But this second factor could be a 0 as well. So when what x value gets it to be 0, then this third factor could be 0. What x value gets it to be 0? So we find all of those. Okay. So with this polynomial, let's set each factor equal to 0. X minus 1 equals 0. Now, solving that first one, 5x squared is equal to 0. I'm going to divide by 5. X squared is equal to 0. And then, how would I solve that? Technically, square roots. I should put the plus or minus in front of that, but we know that 0 doesn't have plus or minus, right? So it goes away, and it's just x equals 0. Now, the interesting part of this is the fact that that 0 counts twice. It has what's called a multiplicity of 2. Why did it count twice? Where did that 2 come from? The exponent on that x squared. Because it came from an x squared, it has a multiplicity of 2. Okay? Let's solve the second one. That's supposed to be an x plus 2. I didn't get my plus sign finished there. There we go. Subtract the 2, and I'm finished already. X is equal to negative 2. Did that factor have an exponent on it? No. So it doesn't. It has a multiplicity of 1. It only counts once. Okay. Last factor, 2x minus 1, I'm going to solve it. 2x is equal to 1. You can probably do this in your head. X is a half. What is the multiplicity for that? 4. because that factor had a fourth power on it. Okay? How many answers do I have here? I've got this one that counted once, this one that counted twice, that's 2, 3. This one that counted 4 times. So 1, 2, 3, 4. I got 7 answers. They're repeated. The 0 was repeated, and the 1/2 was repeated. Now, here's how this relates. So when we're talking about a polynomial, the multiplicity. So there's a right there, multiplicity. Amazing. The number of times a particular root appears as a solution of the polynomial equation. Okay, so read over there in the example. It says a root with even multiplicity causes the graph to touch the x-axis and turn around. It doesn't cross the x-axis, it only touches it. So if I were to graph that polynomial, I want to do that. I'm going to graph 5x squared, parentheses x plus 2, parentheses 2x minus 1, close parentheses, raised to the 4th. I should see it crossing the x-axis at -2 and touching the x-axis at 0 and -1/2. It's going to be hard to see because the resolution is kind of tight here. I'm going to zoom in so we can see what's going on there. We see it crossing at -2. The multiplicity of the -2 was 1. That's an odd multiplicity. Odd multiplicities cross the x-axis. Maybe we're going to write that down in our notes real quick. Odd multiplicity crosses the x-axis. Even multiplicity touches the x-axis. Okay, so I'm going to zoom in a little bit there so we can see that happening there close to the origin. A little harder to see. All right. Zoom in a little bit more. All right, so I zoomed in quite a bit there. You don't have to zoom your graph in. I just want to show you. Right there at 0, this is the origin. That's the axes coming together there. Right there, we see the graph coming down and touching the x-axis and coming back up. It didn't come back up high, but it came back up some. And then it comes back down and bounces off or touches the x-axis at the 1/2 there. If I were to, if I'm at zoom 6, that's a little harder to see. But with the equation, because I know the multiplicity was even, I know it should touch the x-axis at 0 and touch the x-axis at 1/2 and back. And it's like bouncing off of it. That's the way I always think about it. Y'all remember doing that in Algebra 2? We talked about that some in Algebra 2. It's a bigger emphasis in college algebra 4. Okay? So that multiplicity affects the graph. Even multiplicity touches or bounces off the x-axis. Odd multiplicity crosses. That's going to be helpful when we start looking at a graph and having to build an equation from it. That's coming up. Okay, so all right, let's do another one. G of x is equal to x plus 1 squared, x minus 2 cubed. Or maybe a little easier one. Could you tell me the degree of this polynomial? Sorry. Because it's in factored form right now. So degree comes from standard form. But I don't really want to multiply it all the way out. So if I were to multiply out the x plus 1 squared, and I multiplied out the x minus 2 squared, what would the first term of the x plus 1 squared be? Be a positive x squared, wouldn't it? And the first term of this would be positive x cubed. What's x squared times x cubed? X to the 5th. The degree is 5. What's 3 plus 2? All right, so the degree would be 5. Okay, so if you ever get asked the degree, think about what would the first term be if I multiplied it out all the way? What would the exponent on the variable be? All right, so let's get our zeros. So we set each factor, x plus 1 equal to 0, x minus 2 equal to 0. They're giving them to us in factored form today. That's nice of them. They won't very much longer, okay? So I got x equals -1. I got x equals +2. What's the multiplicity on the -1? 2. And I'm just going to abbreviate multiplicity by writing MULT 2. -1 has a multiplicity of 2. So I know the graph of this polynomial should be doing what at -1 on the x-axis? Either coming down to -1 and touching and going back up, or coming up to -1, touching and going back down. Okay. What's the multiplicity on the 2? 3. Multiplicity 3. Because the multiplicity is 3, what do I know the graph is doing at 2 on the x-axis? Crossing the x-axis, because the multiplicity is odd. Odd multiplicity crosses, even multiplicity touches. The degree was 5. How many answers did I have? 5. The -1 counts twice. The 2 counts 3 times. That's a total of 5. Degree and number of answers you have always goes together. They're always the same. If you want to verify that, graph that sucker. Parentheses x plus 1 squared x minus 2 cubed. It comes up and bounces off at -1, goes back down here, turns around, 2. There's it crossing at +2. That makes sense what we're talking about, tying it all together, the graphs and the equations. Okay. All right. Let's go the other direction, and let's start with the zeros or the x-intercepts and build a polynomial. So changing the rules here or going in a different direction. So let's form a polynomial of degree 3 with real zeros, -3, 2, and 5. Write in standard form. That's going to be your favorite part. So what's the multiplicity on each of those if it doesn't say anything? 1. If there's a multiplicity, it's going to have to tell you that. It'll put in parentheses beside it multiplicity 2 or multiplicity 3, whatever it is. Right? So if I know those are real zeros, then I know they came from factors. What are the factors for each of those zeros? Yeah. Swap the sign. Really simple, easy thing to do. And now that's in intercept form. We're from quadratics, but this is a cubic. But it's in intercept form. We want it in standard form. So what do I need to do? Multiply that out. And it doesn't matter what order you decide to multiply that out in. My habit is to do these two together first and then multiply by x plus 3 after I'm done there. Some of you may be able to multiply all 3 of them together at once. I'm not one of those guys. I can't do that. It just doesn't work for me. I always make a mistake if I try to do that. So I'm multiplying out x minus 2 times x minus 5. That's going to give me x squared minus 7x plus 10. That's coming from x times x is x squared. X times -5 is -5x. Negative 2x, that's the negative 7x together. Negative 2 times negative 5 is positive 10. If you need to write that extra step in the middle there, do it. Okay. Next thing would be distributing the x plus 3 to all of that. So x times all of that is going to be x cubed minus 7x squared plus 10x. 3 times all of that is going to be 3x squared minus 21x plus 30. And I'm just stacking up my like terms there is what I'm doing. Instead of writing it out really long, save a little space, stack it up. And then the final answer in standard form is putting that all together. X cubed minus 4x squared minus 11x plus 30. How can I guarantee that that is the right polynomial? Graph it. X raised to the third, right arrow key to get out of the exponent, minus 4x squared minus 11x plus 30. Hit graph, and it should be crossing the x-axis at negative 3, check, positive 2, check, positive 5, check. There is absolutely no way that you could make the right mistakes to make a polynomial that crosses in those 3 correct places and it's not the right polynomial. There's mathematically, the odds of you doing that are probably about the same as winning the Powerball. It's not very likely. Probably not the same, but it's, if you halfway know what you're doing, there's no way that happens. Okay. All right. Let's do another. Form a polynomial. With zeros, negative 4, 2, multiplicity 2, and negative 1, multiplicity 2. In standard form. Okay. They didn't tell me what degree it should be. From the zeros, what degree should it be? 5. You got 2, 4, 5. Multiplicity of 2, 2 of them. Multiplicity of 2 again, that's 4. And then the negative 4 out here has got a multiplicity of 1, so that's 5. So when I get done, I should have something that has x to the 5th power. Okay? So just tying it all together. So what are my factors for this polynomial? X plus 4, x minus 2 squared, x plus 1 squared. All right, so there's factored form. Now, multiplying that out. As the great Johnny Cash song says, you build it one piece at a time. And it didn't cost me a dime. Y'all, you got to YouTube that song if you never heard it. He works at a Lincoln factory making Lincoln cars. And he works there for decades and steals parts for the car, one piece at a time. Sneaks them out in a big lunchbox. And for the big parts, they used his buddy's RV as they parked in the parking lot. And in the song, they end up with a Lincoln built that's it's like 12 different year models all mixed into one car. It's pretty funny. It's just hilarious. All right, so we're multiplying that out. I'm going to start with the ones that are alike first, because that just seems to me like a good idea. So I'm going to go those two at x plus 1 together, and then at x minus 2, those two together. I'm going to get those two going. So that's going to be x squared plus 2x. That's going to be x squared minus 4x plus 4. And then I've still got the x plus 4 hanging in the front there. A lot of operations there. You think about how many operations this is. It's 1, 2, 3, 4, 5 operations just to get that trinomial. Then there's 5 more to get that trinomial. So that's 10 operations so far. Now let's multiply the two trinomials together. All right. X squared times x squared, that's x to the fourth. X squared times 2x is plus 2x to the third. X squared times 1 is x squared. Then I'm going to multiply the negative 4x. So that's negative 4x cubed. That's negative 8x squared. And then that's negative 4x. And then I'm going to multiply the 4 times all of that. So that's 4x squared plus 8x plus 4. And I still got the x plus 4 there. So how many operations is that? 3, 6, 9 to multiply it out. And now I got to put it add it together. So I got x to the fourth minus 2x cubed minus 3x squared plus 4x plus 4. So 9, 10, 11, 12 operations just to do that. Plus the 10 we've already done. That's 22 operations so far. Isn't this fun? So we're at 22 right now. Let's go another step. Multiplying everybody by the x in the x plus 4. That's going to get me to my x to the fifth power, so I feel like I'm on the right track. So that's x to the fifth minus 2x to the fourth minus 3x cubed plus 4x squared plus 4x. Then you multiply everybody by the 4. So that's plus 4x to the fourth minus 8x cubed minus 12x squared plus 16x, and then plus 16. And finally, so how many operations is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 more, so we're at 32. Plus, putting it together. Dang it. It's not working right. Put that thing together, so add the like terms. So I got x to the fifth plus 2x to the fourth minus 11x cubed minus 8x squared plus 20x plus 16. There's my standard form polynomial. So I had 32, 33, 34, 35, 36. 36 operations there to get that done. There's a lot of places you can make mistakes. That's the whole idea. What I'm trying to get you to, you've got to take your time and make sure you're watching your signs and make sure your exponent's there. Don't rush through these things because you miss up somewhere. You miss something somewhere up there at step 2. Everything after that's wrong. Okay, so take your time and one piece at a time. Don't try to do it all at once. Now, how can I verify that that's right? Graph that thing. Let's graph it. X raised to the fifth plus 2x raised to the fourth minus 11x to the third minus 8x squared plus 20x plus 16. I know that thing should be doing what at -4 on the x-axis? Crossing. What should it be doing at +2? touching. What should it be doing at -1? Touching. So over here, this is -1. That looks like touching. This is +2. That looks like touching. 1, 2, 3. There's -4. That's crossing. Not much chance that if we made a mistake somewhere along the way, that it still does all of those things. It might do some of them, but it won't do all 3 of them. Okay, if we've made a mistake. Okay. So that graph is tied together with this stuff really, really nicely. All right. Now, let's build us a polynomial from a graph. Build the polynomial from the graph. So I'm just going to draw a little coordinate plane here. You're just sketching it. You don't have to make it perfect. I will label the points we need. There's just a coordinate plane. X and Y axis there. Fun stuff. That point we're going to call -5, 0. I'm going to call this that. What do I have to call that? 0, 0. I'm going to call that 7, 0. And then I'm gonna pick another point here. I'm gonna let's do that one. We'll call that 3, -2. I'm gonna draw the polynomial. There's my polynomial. Layer on that in, so it looks like it's going on forever there. So based on this picture, so when I build a polynomial, it's built related to the factors. So what do we know about the factors for this particular graph? Even. So if we're going to build a polynomial, we probably want to build it as small as we can, because we don't want a huge polynomial here. What would be the least degree of that? 2. Even. It's even because why? It touches. So we know that the factor that goes with -5 has a squared on it. So I'm going to start there. My polynomial, the factor that goes with -5 is going to be x what? Plus 5. And it's squared because it is touching the x-axis. Now, what do I know about the factor that goes with this x-intercept? It might just be x, because if the factor is got a solution of 0, then it should be just x. We know it has an odd degree because of the polynomial, or because it crosses the x-axis. It's got an odd multiplicity. We're going to do the least odd multiplicity that we can, which is 1. This point we're not using yet because it's not an intercept. Okay, we'll use it in a minute. And then what's the factor there, and what kind of multiplicity does it have? X minus 7, and it has multiplicity of, it's 1. It's odd. We could stretch it out and say that it's 3, but we're going to make it the smallest we can. So that's going to be our factor for x being 7, the x-intercept of 7. Okay, so there are our factors. Now, that other point comes into play in the fact that you've got a leading coefficient that kind of decides how much that polynomial stretches and flexes. So you got an a value that should be going there, like a leading coefficient. Like in polynomial or in quadratics, we had that a that was in the front. That's what this other random point is. It's going to help us find that. Okay? So let's try to find out what A is before we multiply this whole thing out. So how do I do that? How did we do that back in chapter 4? Yeah, so negative 2 goes in for y, and then we have A times 3, 3 plus 5 squared, 3 minus 7. Going to be kind of weird here, but that's all right. So that's going to be A times 3 times 64 times negative 4. 3 times 64 would be 180 plus 12 would be 192 times negative 4 would be negative 400, and then 4 times 90 would be 360 plus 400, 760 plus 16 be negative 676. 768. I missed my 100 there. I'm sure you're right. 3 times 64 times negative 4. 768. A. That's going to be a weird A. Divide by negative 768. Negative 2 divided by that. And then math, enter. Get the fraction 1 over 384. So that's my A value. Well, I randomly picked that 3 negative 2. I didn't have that one planned out before thing. I just made it up on the fly. Didn't pick a very good number there to make it work out pretty. But that's okay because not everything works out beautifully like we try to make it do in math classes. All right, so now let's build the polynomial. So we know that we've got f of x equals 1 over 384 x plus 5 squared x minus 7, right? That's what we had up there. Yeah, x plus 5 and x minus 7. So we're going to multiply that out into standard form. So x plus 5 times x plus 5, and then we got that x minus 7 that's got to go in there. And we got the x and the 1 over 384 that's got to go in there. So that's 1 over 384. I'm going to do that. Fraction is happening last, I promise. I'm not doing that. So that's x squared plus 10x plus 25. So I'm just multiplying those that look alike together first. And then I'm going to multiply by the x minus 7. X cubed plus 10x squared is 25x minus 7x squared minus 175. Nope. Minus 70. Minus 175. And then we still got that times the 1 over 384x at the end. 1 over 384x x cubed plus 3x squared minus 45x minus 175. And then multiply that out. So we're just going to get fractions there. 1 over 384 x to the fourth plus 3 over 384 x to the third minus 45 over 384 x squared minus 175 over 384 x. No, it's just long. None of the math is hard. It's just long. And there's a lot of operations and tons of opportunities to screw it up. As my dad said, don't screw it up. Now, how could I verify? Calculator and graph that. See that it crosses the right places. See that it goes through the 0.3 -2. Okay. You can use that graph to help you. Okay. All right. Next thing is probably that may be the most difficult thing that we do today. The next thing is really easy. It's called turning points. And if you, it's on. I don't think it didn't. Yeah, there it is. It's on toward the bottom there. Turning point is a point on the graph where the polynomial changes from an increasing to a decreasing function, or decreasing to increasing. It changes direction. That's what a turning point is. Okay, so turning points. A polynomial of degree n can have, what happened there? Have at most n minus 1 turning points. So whatever the degree is, the maximum number of turning points is degree minus 1. In calculus, you learn how to find those exact turning points. We can find them with the calculator in college algebra. In calculus, you learn this thing called a derivative, and then you can take a derivative and set it equal to 0, and that'll help you find those turning points and actually find the x values algebraically instead of with the max and min tool on the calculator. So the maxes and mins that we were finding, it's really like localized vertex for a polynomial. So when you look at that graph we started with there, this is a turning point right here because it goes from a decreasing function to an increasing function. There's another turning point right there. We don't know what that point is, but it turns from an increasing to a decreasing function. And then here at the point -3 -2, that's a turning point where it changed directions and went from decreasing to increasing. That's what a turning point is. The only thing you're going to have to do in college algebra is know how many turning points you could have. It's always degree minus 1. This one had 1, 2, 3 turning points, but the degree of the finished polynomial was what? 4. 4 minus 1 is 3. It had the maximum number of turning points. They don't always have that many turning points. Sometimes they do, sometimes they don't, but they will never have more than n minus 1, degree minus 1 turning points. That's what you've got to know. Okay, so let's look at an example. Example H. How many turning points could f of x equals 10x to the 5th plus 5x cubed minus 8x squared plus 4 have? 5 minus 1 equals 4. Degree was 5. Degree minus 1 is 4. That's how many turning points it could have. That doesn't mean it will have, but it could have. Okay. Mr. Isbell, that's too easy. Give me something more difficult. Okay. How many turning? Yeah. Let's make it harder, JC. That's kind of like. How many turning points? What'd you say? 5? Why?
3 plus 2 plus 1 plus 6 subtract 1, that's 5.
Yeah. So degree of this polynomial, you have the x squared. If you multiply this out, you're going to have x cubed. So 5x squared times x cubed is x to the fifth, and then one more x, multiply that together, that's going to be x to the sixth. So the degree is 6. Turning points, 6 minus 1 is 5. Let's do one more. See if I can make it even harder. X squared minus 7 to the third power, x plus 5 squared, and 10x squared. So what's the degree? Degree is 10. Because if I cube x squared, that's x to the sixth, right? And then x to the sixth, and then I square this, that's x squared, so that's x to the eighth. And then another x squared, that's 10. So the degree is 10. So degree minus 1. So our turning points would be 10 minus 1 is 9. That's as hard as it gets. I can't make it any harder than that. That really is as hard as the turning point sparks get.
Maybe that's all.
I'll miss that question.
Maybe that's 7 of those on the quiz. Y'all want 7 of those on the quiz?
Yeah.
6 or 7. All right. Last thing is in behavior. So we got that on our. We saw that when we were talking about the degree and the leading coefficient. They affect the end behavior. End behavior is the trend of the polynomial at the positive and negative infinity parts. So it's the extreme ends. Left side, right side. Left side, right side of the polynomial. That's what end behavior is. I'm going to draw a little chart for us. That's how I'm going to organize my work, is with a chart. We probably did. Because that's my brain and how I think. So first column is going to be degree. Second column is going to be leading coefficient. As x goes to negative infinity, that would be left. As x goes to positive infinity, that would be to the right. And then I'm going to use arrows. Not arrows, but arrows. All right. So degree can be 2 types of degree, odd or even. That's the only kinds of degree you have. Okay? If the degree is odd and the leading coefficient is positive, it's going to act like the graph of a line with a positive slope. Dang it, swap colors. I'm trying to be patient here. There we go. Line with a positive slope. Odd degree polynomials act like lines because a line is the most basic odd degree polynomial. The degree of a line is 1 because the y equals mx plus b, that x has an exponent of 1. So it's really a polynomial, but it's degree 1. So any odd degree polynomial, if it's x to the third, x to the fifth, x to the 27th, any odd degree polynomial with a positive leading coefficient is going to act like a line with a positive slope. So as the graph is going to the left toward negative infinity, what's this side doing? It's going down. It's going toward negative infinity. The y values are going toward negative infinity. As the graph goes to the right, the y values are going toward positive infinity. So left side down, right side up. Any odd degree polynomial does that. All you got to have is the leading coefficient and the degree to decide this. All the other stuff in the polynomial, besides the humps and the dips and the peaks and the valleys in between, that's what all the other terms do. The leading coefficient and the degree term decides all of this. Everything else is what happens in between. Okay? So if it's odd degree and a negative leading coefficient, it's going to act like a line with a negative slope. So as the x values go toward negative infinity, that's to the left, the y values are going up. So that's going toward positive infinity. As the x values are going to the right, or toward positive infinity, the y values are going down. That's toward negative infinity. So left side up, right side down. Notice how the ends of odd degrees go in opposite directions. Odd, opposite, O and O. How that together? Pretty simple. Even degree and a positive leading coefficient. The most basic polynomial that we know of with an even degree is from chapter 4, quadratics. Positive leading coefficient was a quadratic that opened up. A was a positive number, it opened up. The vertex was a minimum. As the left side's going, what are the y values going toward? Positive infinity. The right side, positive infinity. Double up. Even degree, they're going the same direction, evenly. Every even degree polynomial, x squared, x to the fourth, x to the 18th, the end behavior is the same if it has a positive leading coefficient. If it's even degree with a negative leading coefficient, the graph acts like a quadratic that opens down. So the y values are going to negative infinity on both sides. Double down. You got to memorize that chart. You probably already have it memorized. I hope. If you don't, it's not much. It's pretty easy. Okay. Let's do a couple examples real quick. I think we're on K. Determine the end behavior. F of x equals 6x to the third minus 105x plus 84x to the fifth. Ooh, that's not a good looking 5. Fix that 5. Minus 5x to the fourth plus 7. So to determine end behavior, you need the degree and the leading coefficient. That's the only two things you need. The rest of it does not matter. What is the degree? 5. So that's odd. So I know my ends are going in opposite directions. Okay. What is the leading coefficient? 84. That's positive. So that I know that as x goes to the left, the y values go down. And as x goes to the right, the y values go up. This is kind of more of a formal way of saying it. The arrows is probably an informal way of saying it. One more. Example L. F of x is equal to -3, parentheses, x minus 4 squared, parentheses, x cubed plus 1 squared. Dang it, Mr. Isbell, this was easy. Why are you making it hard? Again, two things all you need. Degree, leading coefficient. Degree is 6? No. What is the degree? 8. Because when you square the x cubed, that's going to be x to the 6th. When you square the x, that's x squared. So that's going to be x to the 8th. So the degree is 8, which is an even number. What would the leading coefficient be? -3. So that part was easy. So as x goes to the left, y goes down toward -infinity. And good news is because it was even degree, the positive infinity side is going the same direction. Even should always go the same direction. Odd should always go opposite directions. Every time. On the degrees. Okay? Good bit of stuff here. A lot of review. We probably spread that out in Algebra 2 in like 2 or 3 sections. It's one section in this class. So page 341, 17 through 71 odds. And then skip a few and go to 81 through 89 odd for your practice tomorrow. So tomorrow will be a work day over polynomials in section 5.1. This particular chapter, I put together section 5.2 and 5.3 together because it's zeros of polynomials and you're actually having to figure those out and do synthetic division and all that fun stuff that we did. So I put 5.2 and 5.3 together because they're the same thing. Only difference is in 5.3 it puts the complex in there. So we just put it all in there at once. And then when we get to the rationals in the second half of the chapter, I put a couple of sections together there. So there are 5 sections in this chapter, but I teach it like there are 3 sections in this chapter. So you know.
Wait, so tomorrow we're going to do synthetic division?
No. Tomorrow